Okay, so it's my pleasure today to introduce Diana Chu. I hope I'm pronouncing that right. And who is joining us from Yale, from the Department of Mechanical Engineering and Material Science. Diana also did her undergraduate work at Yale in 2011, and then she did her PhD at UC Berkeley with Stephen Louie in 2017. And then spent a few years as postdoc at Lawrence Berkeley National Lab before going back to her alma mater and joining the faculty there at Yale. She had already had numerous awards. During her student time, she was awarded a Packard Fellowship from the Packard Foundation and other things, and she was named a Rising Star in Physics in 2018. And last year got a DOE Early Career Award, and she already had another NSF report award. So she's been active in the field of excitons in semiconductors and two-dimensional materials, and in particular on exciton dynamics. And that's what she will tell us about that whole story today. So take it away, Diana.
Thank you, Walter, for the kind introduction, and thanks everyone for the invitation to be here today. So today, as Walter said, I'd like to tell you all about some of our recent work on exploring many-body effects on the dynamics of optical excitations in low-dimensional materials. So as many of you are no doubt familiar with, the isolation of graphene in 2004 kicked off the search for all types of other two-dimensional or quasi-two-dimensional materials. And for the most part, these are layered materials that are covalently bonded in the plane with weak van der Waals coupling between layers, so that a single or a few atomically thin layers can be easily peeled off. And by now, a huge family of these types of 2D materials have been discovered. This is just a very small sample of them. And their properties range from semi-metallic graphene to semiconductors like black phosphorus, whose layer-dependent band gap spans the telecommunications spectrum, to large band gap insulators like boron nitride. And so it turns out one of the many reasons that people are so interested in these 2D materials is because they exhibit very interesting optical properties. So one very well-studied family of materials are these transition metal dichalcogenides, or TMDs, which exhibit something called valley-selective circular dichroism. That is, they have two degenerate but inequivalent valleys in momentum space called K and K prime. And spin in the out-of-plane direction is a good quantum number in these valleys. So each band has a well-defined spin with opposite spin in opposite valleys. And then due to the threefold rotational symmetry of these materials, each valley is only going to absorb a single circular polarization of light. So if, for instance, if you shine right circular polarized light, you'll excite an electron and a hole in one valley, and if you shine left circular polarized light, you'll excite an electron and a hole in the other valley. So you get this coupling of spin, momentum, and optical helicity degrees of freedom. So more generally, 2D materials and other types of low-dimensional materials exhibit very strong interactions between this optically excited electron and hole. And the negatively charged electron and the positively charged hole can form a bound state known as an exciton. And in the usual textbook picture in condensed matter, these excitons are typically treated like hydrogen atoms because you have an interacting positive and negative charge. But in low dimensions, the excitation spectra of these excitons actually turns out to be highly non-hydrogenic. And the reason for this is because in low dimensions, the screening environment is extremely inhomogeneous. You don't really have a well-defined macroscopic dielectric constant, because if you sort of think in terms of just field lines between some charged particles, you can imagine there are some field lines inside the material and some field lines outside of the material. So the screening that the charges see is going to depend very sensitively on the length scale in question. And this sort of inhomogeneous screening also means that you can tune the strength of interactions inside these materials by changing the external environment either by encapsulating or stacking different 2D materials together. And this sort of stacking, and also recently adding the additional degree of freedom of twisting, is currently a very active field of research. So hopefully that just gives you kind of a bird's eye view of the field of optics of 2D materials. So sort of what my interests and my field of research is focused on calculating the optical properties of materials. And by now, excitons in low dimensional materials in the steady state low field limit are quite well understood. It's been a pretty active field for the last decade, and we have numerous mature computer codes that can do things like calculate exciton excitation energies and optical absorption spectra in the steady state from first principles. So what's next? Well, as theorists, if we look towards experiment for motivation, what we see is an increasing ability to measure optical excitations at increasingly high temporal and spatial resolution, and also observe interesting transient effects at high pump fluences. For instance, transient photoluminescence reveals this sort of ring-like diffusion pattern for excitons in monolayer tungsten disulfide, and this has been attributed from theory to both phonon wind and Auger processes. And there's also a lot of interest in this ultra-fast charge transfer between layers in TMD heterostructures, where there are also a number of different competing theoretical explanations. So from the theory point of view, understanding these types of experiments are going to require a very detailed description of the dynamics of the optical excitation. And this is something that's still incredibly challenging to address using current first principles techniques. So when it comes to understanding dynamical processes, we're going to need a couple of basic building blocks. So first of all, we need the exciton band structure in order to capture the entire phase space of momentum conserving scattering processes. Then we need some description of the irrelevant scattering matrix elements, or selfenergy. And we also need some sort of equation of motion describing the time evolution. So today I'm going to present some of our recent work along these directions, developing new methods and theories for studying exciton dynamics. So we'll take a look at how to calculate the exciton band structure and its relation to exciton transport. Then I'll tell you about some recent work on exciton-phonon interactions and how to obtain optical line shapes and lifetimes from first principles calculations. And finally, I'll tell you about some in-progress work on the dynamics of very high energy excitons excited in X-ray absorption spectroscopy. But first, since this is a seminar with a broader audience, before getting into the details of these new techniques, I'd like to first take a few minutes to introduce the baseline first principles calculations that we're going to use to build our later understanding on top of. So if we want to understand the properties of a material, we might consider writing down a Hamiltonian that describes all of the interactions of the particles in the material. So we can write down the kinetic energy of the electrons and ions, and also the potential energy, which is just the Coulomb interaction between all the electrons, all the ions, and between the electrons and ions. And then we can imagine just taking this and solving the Schrodinger equation. However, in a real material, the number of electrons and ions is on the order of Avogadro's number. So as straightforward as this sort of approach might seem, it's not something that's actually solvable. And frankly, if we had a computer the size of the Earth and we could actually solve this problem, the result would still be probably such a complicated mess that it wouldn't be that informative. So as you know, much of condensed matter physics is really preoccupied with finding approximations to this many-body Hamiltonian. And one very successful approach introduces something called a quasiparticle. So instead of considering this many-body system, let's just think about what happens when we add one extra electron to a system with n electrons in its ground state. So this electron is moving through the system, and it's interacting with all of the n other electrons in a very complicated way. But since the electrons repel each other, overall, there's going to be a region of positive charge that builds up around our electron. And this positive charge is going to act as a buffer that screens the electron from interacting as strongly with other electrons in the system. Thus, if you sort of treat this electron plus the screening cloud as a single fictitious particle, which we'll call a quasi-electron, you can actually describe this problem of n+1 interacting electrons as a single quasi-electron moving through free space, and this quasi-electron will have a different energy and effective mass than the original bare electron, and since it's not an exact eigenstate of the system, it will also have a finite lifetime. So in order to do this, we first need a good description of the ground state, which we obtain from density functional theory. And today I won't get into the details of that. But once we have the ground state from DFT, next we need to figure out the energy of adding or removing an electron from the ground state. And the amplitude of adding or removing an electron is given within the Green's function formalism by the interacting Green's function G. And if we solve the Dyson equation for this Green's function, we find that it has a pole at the energy of the quasiparticle. And this quasiparticle energy is the sum of the energy of the non-interacting particle plus the energy due to the interactions. And here, the sort of interactions we consider are the electron creating the screening cloud, and then the screening cloud acting back on the electron. So in a sense, the electron is acting on itself. So we refer to this as the self-energy. Of course, up to this point, we haven't really shed any light on these interactions. We've just shoved them all inside this self-energy. So next, we need some approximation for this self-energy. And if we're interested in electron-electron interactions, what we can do is expand the self-energy in a series of the screened Coulomb interaction, W, and then truncate the expansion at the first term. So the self-energy is approximated as the Green's function G times the screened Coulomb interaction W, giving us the so-called GW approximation. And finally, we can construct all of these terms from ab initio. That is, we can construct both the Green's function and the polarizability that goes into the screened Coulomb interaction from the DFT wave functions. And this allows us to proceed with calculating the quasiparticle energies without requiring any sort of empirical fitting parameters. So this is for these single particle, quasiparticle excitations. Next, we want to understand what happens during an optical excitation process. And to consider optical properties now, we really have to think about two particles, because what we have is a photon coming in and exciting an electron and a hole. And the electron and hole can interact, forming a correlated state known as an exciton. So you can think of this exciton in terms of some combination of correlated transitions between the valence band and the conduction band, where the exciton wave function can be written as a combination of electron and hole wave functions with some amplitude A. Alternatively, you can also think of this as some particle that's being excited out of the ground state, and it has some dispersion. And depending on the strength of the electron-hole interaction, you can get a number of discrete bound states, as well as a continuum of states where the exciton continuum corresponds to the quasiparticle band gap. So to describe the exciton, we need to solve an equation for the electron-hole correlation function L. And this is known as the beta-salpeter equation, or BSE. You can see it has the form of a Dyson equation, and with this kernel K playing the role of the two-particle self-energy. So when solving this in practice, we recast the BSE as an effective Hamiltonian, where the eigensolutions are the exciton wave functions, and the eigenvalues, omega here, are the exciton excitation energies. And the BSE Hamiltonian has a kinetic energy term here that describes the transition energy between the quasiparticle bands, and then also a potential energy term describing the interaction of the electron and hole. And this interaction kernel has, again, two contributions. There's a direct term that describes the attractive interaction between the negatively charged electron and the positively charged hole, which is mediated by the screened Coulomb interaction W. And then there's also a repulsive exchange term that's mediated by the bare Coulomb interaction. So now that we know how to calculate exciton energies, we can calculate not only excitons that are excited by light, which carry a very small momentum, since the momentum of visible light is very small, but there's actually an entire energy momentum dispersion or band structure for the exciton. So next, let's take a look at what the exciton band structure looks like in different dimensions and the consequences of the exciton band structure for exciton transport. So in the literature and also in textbooks, it's quite common to consider exciton dispersion in either the Frankel limit, where the exciton sort of hops between discrete levels, or the Wannier limit, where the exciton dispersion is parabolic with an effective mass that's equivalent to the sum of the quasi-electron and quasi-hole band masses. But these assumptions, as useful as they are, leave out a lot of information about the symmetry and dimensionality and overall structure of the crystal, which is really essential when we're considering dynamics, because they're going to dramatically modify the density of states that's available for scattering. So now, just as it's possible to calculate electronic band structures with well-established first principles methods, it's also possible to calculate exciton band structures from first principles. So let's start by considering how the exciton band structure calculated from first principles changes as you change dimensions. First, as an example of a three-dimensional system, this is the exciton dispersion in crystalline pentacene. The dark blue bands here describe dipole forbidden excitons, and the light blue bands describe dipole allowed excitons. And you can see the dipole forbidden band is parabolic and continuous, whereas the dipole allowed band has this jump discontinuity at the gamma point. Now, going down to two dimensions, this is the exciton band structure in monolayer MOS2. You can see a V-shaped upper band that's degenerate with a parabolic lower band at the gamma point. And another two-dimensional material, monolayer black phosphorus, exhibits the linear dispersion along one direction from gamma to X, and a parabolic dispersion along another direction from gamma to Y. And then finally, going down to one dimension, this is the exciton band structure in a single walled 8-0, in an 8-0 single walled carbon nanotube. And again, we see the dark blue dipole forbidden exciton bands are parabolic, but this light blue dipole allowed exciton band appears to have a small cusp at the gamma point. So from this, it seems that exciton band structures in 3D, 2D, and 1D all exhibit some sort of discontinuity at the gamma point for the dipole allowed excitons. So now let's take a look at where these discontinuities are coming from. So it turns out that these discontinuities are all coming from this electron hole exchange interaction, which I showed you before in the BSE Hamiltonian. And this discontinuity essentially arises from the behavior of the electron hole exchange in the long range or small q limit. And here I'm going to use this capital Q to represent the exciton's center of mass momentum. So in the small q limit, the exchange term goes as this dot product of the center of mass momentum with this matrix element, with this dipole matrix element between the exciton state S and the ground state. And then this is multiplied by the Fourier transform of the Coulomb interaction, V of Q. So in 3 dimensions, the Coulomb interaction goes as 1 over q squared, which means that the long-range limit of the exchange goes as a constant times cosine squared theta, where this angle theta is the angle between the exciton's momentum and the dipole. So from this, we can really understand the band structure that we see in pentasy. For a dipole forbidden state, this exchange interaction is 0. So the band is parabolic and continuous, reflecting the parabolic underlying electron and hole band structure. But for the dipole allowed states, when the momentum is parallel to the dipole, this exchange term is constant and non-zero, giving you this higher energy longitudinal exciton band. But when the momentum is perpendicular to the dipole, this exchange term is 0, giving you this transverse lower energy exciton band. So this gives you this well-established energy splitting of the longitudinal and transverse exciton states with a jump discontinuity at the gamma point. So next, let's consider the 2-dimensional picture, focusing on monolayer black phosphorus. So in 2 dimensions, if you take the Fourier transform of the Coulomb interaction, it actually goes as 1 over q. So the long-range exchange goes as the absolute value of q times cosine squared theta, where again, theta is the angle between the momentum and the dipole. So black phosphorus exhibits a linear dichroism, where optical absorption is only allowed when the light is polarized along the x direction. So we can say that the exciton dipole here is oriented along x. And so the exchange is only non-zero when the exciton momentum is also parallel to x. And this is what gives us this linear dispersion along the gamma to x direction. Along the other gamma to y direction, the exciton momentum is perpendicular to the dipole. So this exchange term is 0, giving us a parabolic dispersion along gamma to y. And in monolayer MOS2, the situation is quite similar, only now the lowest energy exciton is doubly degenerate due to the degeneracy of these K and K prime valleys. And this is a problem that we explored actually many years ago in this older work, where we found that the interplay of the intervalley and the intravalley exchange gives rise to 2 exciton solutions. There's a longitudinal solution that disperses as the absolute value of q, giving you this V-shaped upper branch. And then there's a transverse solution that gives you the parabolic lower branch. And one important thing to note is that in 2D, unlike in 3D, the transverse and longitudinal branches actually both can couple to light, because they couple respectively to the longitudinal and transverse components of the in-plane projection of the light. And then finally, if we go down to 1D, we find that the Coulomb interaction behaves as this function containing the natural log of the absolute value of q. So this means that the exchange has a dependence on q squared times cosine squared theta times the log of q. And if we look at the exciton dispersion in the single-walled carbon nanotube, we see for the dipole forbidden excitons, the exchange is 0, so the dispersion is parabolic. But for these light blue dipole allowed excitons, the long-range exchange is non-zero, and you get this cusp-like feature around gamma, which actually fits very well to the function q squared log q. So here, the dots are the explicit results from our first principles calculation, and the dashed lines are the fits to these functional forms from the effective Hamiltonian that we derive. So to summarize, we see that there are discontinuities of different order in the exciton band structure in 3D, 2D, and 1D. And these discontinuities are purely a quantum mechanical effect coming from the exchange interaction, and they can't be understood from the underlying electronic band structure alone. So the next question is, how are these discontinuities going to affect exciton transport? And as a first step to answer this question, we consider exciton transport just in the first few femtoseconds after excitation, that is prior to any sort of thermalization. And in this short time regime, we can treat the exciton as essentially ballistic, and that lets us really zoom in on the direct effect of the features of the band structure on transport. So we start by looking at the time evolution of an exciton wave packet in crystal pentacene, and we initially excite a wave packet of excitons in this dipole allowed branch and in the dipole forbidden branch. And we see that over the course of 150 femtoseconds, the dipole allowed exciton begins to have this asymmetric evolution due to the asymmetry of the underlying exciton band structure. The dark exciton, however, remains essentially non-dispersive on this time scale. Next, we look at an exciton in the V-shaped band and the parabolic band in monolayer MOS2. And we see that for the exciton in the V-shaped band, it develops a node in the exciton density due to the non-analytic dispersion at the gamma point. The exciton coming from the parabolic band, however, remains essentially, again, non-dispersive on this time scale. And for black phosphorus, likewise, this non-analytic behavior at gamma gives rise to a highly asymmetric transport with exciton density spreading along the linearly dispersing direction much more rapidly than along the parabolically dispersing direction. And finally, for the single-walled carbon nanotube, again, we see that the non-analytic dispersion at the gamma point gives rise to some interesting nodal structure in the time evolution of the exciton wave packet for this dipole allowed exciton. But again, on this short 100 femtosecond time scale, the parabolic exciton is again essentially non-dispersive. So to summarize, we see that this discontinuity at the gamma point leads to fast ballistic transport of excitons, about 0.1 nanometers per femtosecond, or 1 × 10⁵ meters per second. And excitons with no long-range exchange component, that is, excitons that are either purely transverse or purely charge transfer-like, can be well approximated as non-dispersive in this early time ballistic regime. So far, I've only showed you excitons in this quasi-ballistic regime prior to thermalization, but of course we know that acoustic phonons are going to very quickly allow for scattering between all of these different exciton branches, and that could potentially destroy signatures of the discontinuity in the diffusive regime. However, we see that even in this sort of simplified picture that I've shown you so far, this initial ballistic regime, what it does is it establishes some sort of non-trivial initial distribution of the excitons, which are going to act as your initial conditions for the later time exciton diffusion. And so it could still be apparent in some features of the diffusion at later times. So now how can we connect this picture of exciton transport in the quasi-ballistic regime with the diffusive regime? So just as a very simple back of the envelope calculation, we know that the diffusion coefficient is related through the Boltzmann transport equation in the relaxation time approximation to the velocity squared times the relaxation time. And we can get the velocity from our exciton band structures, and then we can take some order of magnitude estimates for the relaxation time from the literature. And if we do this, we find values for the diffusion constant for monolayer TMDs and crystal pentacene that are in pretty decent agreement with the range of values for the diffusion constant measured in experiment. Actually, this should not say crystal pentacene, this should say AC molecular crystals more generally, because the experimental data is actually for tetracene. So this is a pretty rough estimate for the relaxation time because they're taken from a couple inconsistent both experimental and theoretical results in the literature. But so to really study exciton diffusion from first principles, what we're going to need to do is to actually calculate the relaxation time from first principles. So now let's go ahead and see how we would approach doing that. So in the next part of the talk, I'd like to take a look at how we can obtain scattering times by calculating exciton-phonon interactions from first principles. So exciton-phonon interactions are really a key component for understanding non-radiative dynamics, decoherence times, temperature-dependent line widths, and exciton diffusion. And they can be probed experimentally using spectroscopic methods like absorption, photoluminescence, four-wave mixing. But reported lifetimes can vary a lot across all these techniques, highlighting the need for accurate first principles calculations. So from first principles, calculations of electron-phonon interactions are, and electron-phonon self-energies built on top of density functional perturbation theory are something that's very well established. So for excitons, you might imagine the simplest first approach might just be to write down the exciton-phonon self-energy Xray as some linear combination of the electron-phonon self-energies calculated from DFPT, weighted by the electron hole amplitude A. And this is an approach that was first proposed by Marini in 2008. And in the past, we've shown that it gives results for monolayer MOS2 that give you pretty decent agreement with experimental spectrum when it comes to the line shape of the calculated and experimental optical absorption spectra. But if you actually look at this equation here, you can immediately see there's a pretty severe approximation in that the self-energy sigma of the electrons and phonons are evaluated of the electron phonon and the whole phonon are evaluated at the non-interacting energy. So this means that the exciton binding energy is actually completely neglected in this approach. And we know in low dimensional materials, the binding energy can be as large as 1 eV. And this approach is also going to give us an unphysical finite lifetime for the lowest energy exciton state at 0 temperature. So how can we improve on this? So more rigorously, you can derive the exciton-phonon self-energy within many-body perturbation theory, as demonstrated in this paper from Antonius and Louis. So here, lambda is the electron hole propagator, including both electron hole and electron phonon interactions. And you can see this equation. It has the form of a Dyson equation connecting this lambda with L, which we saw before was the electron hole propagator from the beta-salpeter equation. And they're connected through the exciton-phonon self-energy Xray. And as usual then, the inverse of the lifetimes is associated with the imaginary part of the self-energy Xray. So to obtain this self-energy, we first need to obtain the exciton-phonon coupling matrix elements, which can actually be constructed from the electron-phonon coupling matrix elements, these little g's here, obtained from density functional perturbation theory. And here, what capital G is describing is the probability amplitude that an exciton S with a center of momentum capital Q is going to scatter into another exciton state S prime with momentum big Q plus little q. And it's going to scatter by either absorbing or emitting a phonon. So that's what this equation here means. And then then we can use this to construct the lowest order exciton phonon self-energy, which is analogous to the Van-Migdal term in the electron phonon self-energy, and can be, so this self-energy Xray is written in terms of the exciton phonon matrix elements, capital G. And here capital omega is the exciton energy, little omega is the phonon energy, and capital N is the phonon Bose occupation factor. And this formalism is something that's attracted a lot of interest in the ab initio community recently. And it was recently applied from ab initio for the first time by the Bernardi group at Caltech to obtain exciton-phonon relaxation times in bulk boron nitride. So inspired by this earlier work, we decided to calculate the exciton-phonon interactions in monolayer MOS2. So this is the calculated exciton band structure, and it's colored according to the relaxation time of each exciton state. The little circles here label the spins of the conduction and valence states making up each exciton. And we see, as expected, the lowest energy exciton state, which is this spin forbidden state at Q equals K right here, has the longest lifetime. And the lifetime is about 100 femtoseconds. Interestingly, however, if we look at the states around the gamma point, we see that this higher energy spin allowed state, the spin allowed exciton state, and this is the one that corresponds to the well-known A exciton in MOS2. This one has actually a longer lifetime than the lower energy spin forbidden state. And this is initially somewhat counterintuitive, but it arises as a consequence of the spin selection rules for the exciton-phonon scattering, which means that excitons are going to tend to scatter within the same exciton band. So the spin forbidden state at gamma can scatter into this lower energy spin forbidden state at K. But for the spin allowed state, the state at gamma is actually already the lowest energy spin allowed state, so it has a longer lifetime. So up to now, what we've been doing is we've looked at the relaxation time using this exciton-phonon formalism, assuming that the exciton-phonon self-energy is diagonal in the exciton states. And this is not necessarily true, especially if the exciton-phonon vertex is roughly the same order of magnitude as the exciton binding energy, it's smaller in MOS2, but it still might be significant. So there's this previous work on the semiconductor block equations, which suggests that in addition to the diagonal self-energy, if you want to look at line widths, you also need to consider some sort of decoherence, which comes from the off-diagonal terms of the self-energy in order to really get an accurate picture of the line widths in the absorption spectrum. So following this work, we actually then went ahead and calculate the line width using both the full self-energy and then compared that against the line width calculated simply with the diagonal part of the exciton-phonon self-energy. And you can see that in order to get good agreement with experiment, it's actually really necessary to include the off-diagonals of the self-energy. And additionally, I really want to emphasize here that this large difference here is really just coming from the off-diagonal terms. The actual exciton-phonon coupling strength used in both sets of calculations are the same. So from this then, how can we really understand what's happening when we include these off-diagonals in the self-energy? So the role of off-diagonals of the self-energy is something that's been discussed actually at length by Toyozawa 50 years ago, but it's something that's frequently neglected in calculations and really hasn't been considered from ab initio up to this point. So if we think about what's happening, you can think of absorption as a two-step process within second-order perturbation theory, involving both the absorption of a photon into some exciton state S prime, represented by the red line, followed by the scattering through a phonon to some final state S, represented by the blue line. And in the full off-diagonal formalism, the absorption actually sums all of these scattering processes here on the left-hand side of the equation. But you can break up this sum into two components, one just involving the diagonal terms where the initial state S equals the final state S prime, and then the remaining terms involving the cross products of the sum. So if you look at the first term, it actually looks like a sum over a bunch of Lorentzians. So what you can interpret this as is a sort of amplitude of exciting into to an exciton state S that already has some finite lifetime. And no, it's going to give you an absorption line shape that looks Lorentzian. And then the second term, which includes the remaining cross terms, gives you essentially the asymmetric part of the optical line width. So overall, I think this sort of picture, which is established ages ago, gives us a pretty nice intuitive understanding of what we're doing when we include only the diagonal terms of the self-energy versus the off-diagonals. So now I think I'm close to running out of time, but I have just quickly one more topic I'd like to show you guys. So in the previous sections, I told you about the dimensionality and symmetry effects on the exciton band structure. And we took a look at exciton phonon interactions and the role of decoherence in the line shapes of the absorption spectrum. So finally, let's take a look now at sort of a different picture of what happens to very, very high energy excitons that are excited in X-ray absorption spectroscopy. So to obtain X-ray absorption spectra, we can solve the Bethe-Salpeter equation as usual and obtain correlations between the core hole and the excited electron. And some common methods include things like the ocean code, which approximates the hole as a core atomic orbital, and the exciting code from the Draxel group, which recently implemented an all-electron approach to the core level Bethe-Salpeter equation. But one thing that hasn't really been explored in the Bethe-Salpeter equation is, if you have some sort of high energy X-ray, you're not only exciting electrons from core states, you can also excite electrons from valence states to very high energy conduction states. So the question I'd like to address here is, within a Bethe-Salpeter equation approach, what is the effect of coupling between the core level excitations and these excitations to very high energy conduction states? And as an example system, I'd like to start by taking a look at shallow core levels in monolayer MOS2. And this is because we expect that the coupling of the valence and core subspaces is going to be more important in systems where the exciton binding energy is large. And in quasi-2D materials, it's by now well established that excitons at the optical band edge have these exceptionally large binding energies. So we expect that excitonic effects in the X-ray absorption spectrum are going to be similarly large or even larger due to the localization of the core state. So to start, let me show you the quasiparticle levels for monolayer MOS2 before digging into the details of the BSE calculation. So we're going to be mainly interested in excitations from these semi-core states down here. If you sort of zoom in, you can see there's a set of spin orbit split 4p 3/2 states and 4p 1/2 states. And you can see that since these are semi-core states, they're not completely flat, but they're fairly dispersive with a bandwidth and crystal field splitting of about 200 millivolts. So next, we'd like to obtain the X-ray absorption spectrum by solving the Bethe-Salpeter equation. And ideally, what we need to do is actually include all transitions over a range of about 40 electron volts, which is the range from this the 4p to conduction band. However, in this energy range, the number of valence to highline conduction transitions is on the order of about 4,000, which means that it would increase the size of our BSE matrix by a factor of about 16 million, which is not something that's computationally accessible at this point. So as a first naive approach, let's just see what happens if we solve the Bethe-Salpeter equation on a subspace that contains only the 4p states and the lowest conduction bands. So we're just going to throw out all of the valence to high energy conduction transitions for now. And this is the calculated X-ray absorption spectrum within this naive approach. And to use a technical term, it looks a little weird. So specifically, this dashed line here is the GW-RPA spectrum with no electron hole interactions. And the solid line is the GW-BSE spectrum with electron hole interactions. And you can see that the interacting spectrum actually appears to have a smaller oscillator strength and is shifted to higher energies compared to the non-interacting spectrum, which doesn't seem like something that's physical. So we wanted to, so since this result doesn't really look physical, we wanted to go back and look at what was being left out of this calculation, specifically the contribution from the valence level transitions. So now the question is, how can we build an effective Hamiltonian that accounts for the coupling to the valence transitions without increasing our matrix size by a factor of 16 million. So first, let's consider how we partition our Hilbert space. The naive calculation was done in a subspace, which I'll refer to as the A subspace, which includes only these core to conduction transitions. And then the remaining Hilbert space is composed of the B subspace, containing the valence to high energy conduction transitions. And in the electron hole basis, the beta-Salpeter equation is written as an eigenvalue problem with an effective Hamiltonian, and the full Hamiltonian is made up of transitions from the A and B subspaces. And in our naive approach, what we're doing is approximating this full Hamiltonian as just this AA block. And in fact, whenever we solve the BSE numerically, we always have to do this sort of partitioning, where we treat the A subspace essentially as a convergence parameter. So now what we're doing is we're asking the question, how do we handle this sort of numerical partitioning when we can't actually converge the A subspace by brute force? So this sort of subspace projection is one of the most common problems in physics, and we know how to project this larger Hamiltonian onto the A subspace by using Laudine partitioning, which says that we can write the effective Hamiltonian with the same resolvents as the full Hamiltonian as this AA block plus a correction due to the downfolding of the matrix. And this correction describes the coupling of the A subspace through this off-diagonal AB block to the resolvent of the B subspace here. So you can see the magnitude of this correction is going to depend on the relative energies of the A and B subspace, as well as the magnitude of these off-diagonal coupling matrix elements. And if we solve for H effective, then we've essentially solved our problem. But in order to get to H effective, we actually need the full Hamiltonian because we need both the AB block and the propagator on the B subspace. So then the challenge is, how do we construct H effective without explicitly calculating all of these additional matrix elements? And to do this, we're going to separately look at the different contributions to the direct and exchange, to the BSE Hamiltonian coming from the direct and exchange terms. So I'm going to go through this a little quickly since I'm running out of time, but in short, what we see is that the downfolding of the direct term can essentially be neglected due to the orthogonality of the core and valence states. And if we look at the downfolding of the exchange term, it has this form here, the AB exchange block connected by the propagator on B to connected by this other coupling matrix BA. And if we look at this diagrammatically, it's actually very clear what this is. It's just the exchange diagram on the A subspace screened by the electron hole propagators on the B subspace. So we can actually account for the coupling to this larger Hilbert space by screening the exchange term with states that we don't include in our subspace. So if we do that, then, and we recalculate the absorption spectrum of MOS2, we get something that looks more physical. And So after we screen the exchange interaction, we get this very dramatic change in the spectrum on the right. You see what appears to be some large excitonic effects. There's a large redshift of the interacting solid line spectrum compared to the non-interacting dashed line spectrum. And you also have these sharp peaks that look like exciton states. And if we analyze these exciton states, we see that the binding energy of the core excitons is about 1.8 electron volts, which is about 3 times larger than the binding energy of the excitons at the optical band edge. And the radius is about 3 angstroms, which is about 3 times smaller than the radius of the optical excitons. And if you sort of take a look at the exciton wave functions associated with these different peaks in momentum space, you can see the exciton wave function mixes both the K and K prime valleys, and also this 6-fold ring-like valley around the gamma point, whereas for the optical excitons, they only come from K and K prime. But for the core excitons, you get this additional mixing due to the much larger binding energy. And finally, since I'm really running out of time, I just want to show you, we've recently also applied the same approach to look at the X-ray absorption spectrum of liquid water, which is quite exciting because now we've sort of stretched the energy range up to a few hundred electron volts. And here we also see a less dramatic change, but we do see that including this coupling to the valence transitions gives us a much better agreement with the experimental absorption spectrum of water. So I'm just going to skip the summary for now, and just let me and just acknowledge all of my many collaborators. So the exciton dispersion project that I showed you was done in collaboration with the group of Sivan Rafaeli Abramson at the Weizmann Institute. The exciton phonon interactions were done in collaboration with Yinghouse Chan at Academia Sinica, and Jeff Meaton and Steve Louie at UC Berkeley, and also Felipe Jornada at Stanford. The X-ray absorption spectrum work was done in collaboration also with Felipe Jornada and Steve Louie, and the X-ray absorption spectrum of liquid water was done in collaboration with the group of Shifan Wu at Temple University and Roberta Carr at Princeton. So finally, again, thank you for inviting me to be here today, and please let me know if you have any questions.
Thank you very much for a very clear talk, and let's see if there are some questions from the audience, particularly maybe from the students also. So please raise your hand or unmute your microphone if you have a question. Okay, Mandela, I knew I could count on you.
Hello. Thanks for the nice talk. So I have sort of a naive question. Can we, when you're doing many body calculations, do you think of the exciton as like some free neutral boson, or is it like an electron in a whole potential?
So that's actually a very good and slightly subtle question, not naive at all. So you can think of, so the answer is you can think of the exciton as a boson as long as the density of exciton states is not too high. So as long as so excitons do behave like bosons in a sense. You can get Bose-Einstein condensates of excitons, but as the exciton concentration increases, then you get interactions between the individual electrons and holes, and so it's no longer boson-like.
So in like in transport studies where there's this polarization of the electrons and the holes, there would be better to like treat them like fermions, I guess, right?
So I guess in transport studies, if you have if you're looking at transport in an electric field, then I think what you can see is if the energy due to the electric field is large enough to break apart the exciton, which in many cases it is, and then you can treat the carriers as just the electrons and the holes.
I see. Thank you.
Okay. Any other questions? Well, maybe I can ask one, and that is, you talked about this simulations at very short time scale of how these wave packets evolve and this ballistic transport of the exciton. Is that something that is experimentally accessible, or how would one do that experimentally?
Yeah, so I think it's sort of at the very limits of what is experimentally accessible. So recently I've been actually talking to some experimentalists about doing it. And I think in the very cutting edge transient microscopy setups, they can get resolutions of 10 femtoseconds. I think the challenge is getting both the temporal and spatial resolution at the same time, because from what I understand, the setups that give you, the highest time resolution don't have very good space resolution, and vice versa. Mm-hmm. So I expect it should be possible to see within the next 5 years or so, maybe.
Thank you. Yeah, we'll be looking forward to that. Yeah. But you mentioned that it would have an effect later on at longer time scales too, that it would somehow imprint something on the diffusion.
Right. So that's sort of the long range goal of what we're trying to do. So the next step is we actually want to calculate the actual diffusion, including the exciton phonon interactions, by taking this sort of wave packet time evolution and adding in the exciton phonon scattering. So we don't quite have results for that yet. So I'm not sure what the imprint would be. But one thing we do see is this exciton, this non-parabolic exciton band structure gives us a pretty fast group velocity, and what we do see if we just use sort of the linearized Boltzmann transport equation is that the diffusion constants that we're getting out, if we sort of trust the relaxation times that are reported in the literature, then they require a group velocity, a band velocity that's quite large and consistent with our calculations of exciton band structure.
Okay, thank you. Any other questions? Yes, Xray.
Hi, Dana. Thanks for the nice talk. I have a question on you mentioned that like the monolayer MOS2, it has A exciton and also B exciton, and there's a Vallée dependence K prime. And what's so what's the origin of that A and B excitons? Does that depend on the spin-orbit coupling?
Yes. So essentially, the A and B exciton are coming from the spin orbit coupling. So the A exciton comes from the lowest energy transition here between, let's say, the blue bands and so it comes from the lowest energy transition, and then the B exciton is the spin orbit split transition. And then the A exciton is doubly degenerate. So it contains both this blue band to blue band transition at K and red band to red band transition at K prime.
Right. Well, what about the spin structure in this in A exciton and the B exciton? So is it possible that we can distinguish them by excite the excitons using polarized light and through some spin transport? I'm interested in spin tronics. Yeah.
So yes. In order to distinguish them, you can't just sort of, as you were hinting at, you can't really distinguish them within optical absorption because you're exciting both the degenerate valleys. But you can distinguish them in the photo emission. So if you shine light of one circular polarization, the photo emission maintains much of the same circular polarization, and the other way is through some sort of spin transport, like a quantum spin Hall effect, which also in this case, because you have different spins in different valleys, becomes a valley spin Hall effect.
I see. Thanks.
So to follow up on that, you had a picture where you had not only the A and the B, but then an A prime and B prime and so on. Are those just the higher Rydberg series of the A and the B?
So yes, thanks for pointing that out. So yeah, I didn't have a chance to get into this, but those are exactly the higher Rydberg series. Yeah, and they are, and you know, they're the Rydberg series, but they don't follow the usual Rydberg energies. So A prime is 1s, and A double prime is 2s.
So how do you?
A is 1s, A prime is 2s, A double prime is 3s.
So how do you? This is maybe a bit of a technical question, but when you get this out of use BSC equation, how do you see that this is a 2s and, for example, not an exciton related to this other conduction minimum that you have between gamma and K? There is people already in the beginning, when the band structure of molybdenum sulfide wasn't so well understood, people were speculating that you could also have excitons at this other conduction band valley and how it would interfere. So how do you know that this A prime is a 2s exciton?
That's a good point. So essentially what we do is we look at the exciton wave function, and we characterize them as 1s, as this Rydberg series based on the nodal structure of the exciton wave function. So actually, I don't have that in a slide here, but it's from the wave function. It's very, very obvious. And another way you can characterize also the angular momentum of the exciton wave function is by looking at transitions. So here I was saying, A prime, A double prime are the sort of the 1s, 2s, 3s states, because the s states are the ones that are bright under single photon absorption. And then you can also, there are also dark, 2p, 3p, and 3d states, which are dark under single photon absorption. But if you simulate 2 photon absorption, then you can actually see bright transition from the 1s-like state to the 2p-like state. And also in experiment, they've been able to do 2 photon absorption and see transitions to p-like states that are in really good agreement with calculations.
Okay, yeah, thank you. Well, if there are no more questions, I'll ask once more if this discussion inspired any other questions. If not, then I guess we'll stop the official part of the talk. Thank our speaker again once more.
Yeah.
Unfortunately, the applause is a little bit underwhelming if it's not in person, but I see some hands clapping. And we'll stop the recording and we'll hang on a few more minutes to chat. Okay.
Yeah, and I'm also available by email or Zoom. Feel free to send me.
Okay, thank you for that. Okay, so all right, Shule, are you stopping the recording, or should I do that? Or okay, I stopped it.